Welcome to The Explainer. We build these incredibly complex AI models, but how do we actually know if they're any good? It's a huge question, and today we're going to break down exactly how we figure that out. Let's get into it. So let's just put that big question right out there. You've spent all this time and energy training a model. On your own data, it looks pretty good, but is it ready for the real world? How can you be truly confident it's not going to fall flat on its face?
The easiest way to wrap your head around this is to think of it as quality assurance, or QA. You would never ship a new piece of software or roll a new car off the assembly line without testing it to death, right? Well, AI is exactly the same. Not testing your model properly is a recipe for disaster.
Okay, so before we can even figure out how to get a model right, we first have to understand the two main ways it can be wrong. And what's interesting is that they're basically opposite problems. The real trick is finding the sweet spot right in the middle. Let's use an analogy here, because it makes it super clear. On one hand, you have underfitting. Think of this like a gigantic, shapeless t-shirt that's labeled one size fits all. But in reality, it's so baggy and generic it doesn't really fit anyone well. The model is just too simple. On the other end, you have overfitting. This is like a shirt that's been custom molded to fit one single person's body perfectly, down to the millimeter. It's flawless on them, but it's completely useless for anybody else. The model has basically memorized the data instead of learning from it. So let's put a technical name on that baggy shirt problem. That's what we call bias. When a model has high bias, it's making really simple faulty assumptions. It's just not complex enough to capture the real patterns in the data. And that right there is underfitting.
And that perfectly molded shirt? Well, that's variance. A model with high variance is way too sensitive. It's not just learning the important patterns, it's also learning all the random noise in the training data. So the moment you show it something new, it gets confused. It can't generalize. In other words, it's overfitting.
This really gets to the heart of it. We're looking for that Goldilocks model. It can't be too loose and generic, and it can't be too tight and specific. The goal is to get it just right so it can make smart predictions on data it's never seen before. All right, so how do we actually do that? How do we find this perfect fit? Well, just like a great tailor, a data scientist has a really careful process for measuring, adjusting, and testing to get the final product right. It all starts by being smart about how you use your data. You don't just throw everything at the model at once. First, you take a big chunk, your training data, to build the first version of the model. Then you use a totally separate validation set. Think of this as the fitting room. You test the model on this data it hasn't seen before to see how it does and make adjustments. And finally, you have one more set, the test set, that has been locked away the whole time. This is the final exam, a true, unbiased check on how it'll perform in the real world. Now, when we say we're making adjustments in that validation step, what are we actually changing? We're tuning the model's hyperparameters. These aren't things the model learns on its own. They're the settings the data scientist chooses before the training even starts. They're literally the knobs and dials you use to control how the model learns things, like its learning rate or how complex it's allowed to get. And that whole process of tweaking those knobs and dials, that's called model tuning. It's a loop. You train, you validate, you tune a hyperparameter, and you do it all over again, searching for that magic combination of settings that gives you the best performing model. Which brings us to what might be the single most important concept in all of this. It's called the bias-variance trade-off. See, you can't just get rid of bias completely, and you can't eliminate variance either. It's a balancing act. The goal isn't to hit zero. It's to find the perfect point of compromise between the two.
Let's look at what goes wrong at the extremes. A high bias model is just wrong all the time, in very predictable ways. It fails on the training data, and it fails on new data. It's just too simple. But a high variance model is trickier. It's brilliant on the training data, gets a perfect score, but it fails on new data because it basically cheated by memorizing the answers instead of learning the concepts. It's wrong in inconsistent, unpredictable ways.
So, how do we manage this balancing act? Well, the pros have a master technique that's designed specifically to nail this trade-off. It's called cross-validation,
And it's a much smarter, much more robust way to test your model. The most popular version is called K-fold cross-validation, and it works like this. Instead of just one validation set, you split your data into a bunch of groups, or folds, let's say 5. Then you train the model 5 separate times. Each time you hold out a different fold for validation and train on the other 4. At the end, you average the performance across all 5 runs. This gives you a way more reliable and stable idea of how your model will actually perform on unseen data. Okay, we've tuned our model. We've used cross-validation to find the best settings. We're feeling pretty good about it. Now what? How do we actually put a number on it? What are the scorecards we use to say, yep, this model is a winner? For most classification problems, it all starts with something called a confusion matrix. And we're going to use the greatest example of all time, hot dog, not hot dog. It's simple. A true positive is when it sees a hot dog and correctly yells hot dog. A true negative is when it sees a taco and correctly says not hot dog. The mistakes are where it gets interesting. A false positive is when it calls a taco a hot dog, an annoying mistake. But a false negative is when it sees a hot dog and misses it completely. That could be a really costly miss. And which error is worse really depends on what you're trying to do. And from that matrix, we get our key metrics. Accuracy is just the simple overall how often was it right score. But then we have precision, which answers a specific question. Of all the times we predicted hot dog, how many of them were actually hot dogs? You focus on this when you want to avoid those annoying false positives. Then there's recall, which asks, of all the real hot dogs in the world, how many did we successfully find? You focus on that when you absolutely can't afford to miss one, when you want to avoid false negatives. And if you need one number that balances both, that's the F1 score. It's a beautiful single measure of a model's quality. But look, a fantastic F1 score, as great as it is not the end of the story. Not even close. A model doesn't just exist for its own sake. The real final test is whether it actually delivers value in the real world. This is why you absolutely have to connect all this technical evaluation back to business goals. You have to ask the hard questions. Is this model actually making us money or saving us time? Is it really better than what we were doing before? Is a 95% success rate good enough if those 5% of errors are absolutely catastrophic for our customers? These are the questions that truly matter. And on top of the business questions, there are the practical, real-world technology questions. Seriously, the most accurate model on the planet is completely useless if it's too huge to fit on our servers, or if it takes a month to retrain, or if it needs a supercomputer to give you one prediction. You have to think about its size, its speed, and how much of a pain it's going to be to keep it running and updated. And that really brings us to the final thought here. Evaluating a model isn't something you do once and then you're done. It's a cycle. The world changes, people's behavior changes, new data comes in. Which leaves us with this final big question to chew on. If the world is always in motion, can a model's perfect fit ever really truly be considered finished? Thanks for joining this Explain.